our experiment is determination of conductance of different solutions of different concentration by using conductometer. So this is our instrument which is known as conductometer, and this instrument it is used to measure the conductance of different solutions. Now we have conductivity cell. This is also known as electrode, glass electrode, which measure the conductance of the solution, and that value, that conductance value is displayed over this instrument here. Okay, to perform this experiment we need the beaker, we need graduated flask to prepare the different concentration, and we need distilled water. First of all, we will prepare our master solution. Here I will tell you that how can we prepare the solutions. First we will prepare 0.1 normal KCl, which is our master solution. So to prepare the 0.1 normal KCl, we will use this formula, which is normality, which is equal to x by equivalent mass. What is x? X is the weight of the KCl which we will measure into 1000 by volume. So we are preparing 0.1 normal KCl in 1 liter of solution. So by using this formula, I have calculated the mass of KCl, which is 1.86 gram of KCl. We will dissolve it in 1 liter of solution. So in this way we have prepared our master solution. Now by using master solution, we will prepare different concentrations of KCl. So here we will prepare different concentrations of KCl by using our master solution. Our master concentration of our master solution is 0.1 normal, and the different concentration that we are preparing is, first is 0.01 normal, second is 0.02 normal, and third is 0.005 normal. So to prepare 0.01 normal, we will use this formula. This formula is known as normality equation. So N1 V1 here represent the initial concentration of our master solution, and N2 V2 is the final concentration which we want to prepare. So to prepare 0.01 normal, I have calculated by using this formula 25 ml of 0.1 normal KCl, and we will add 225 ml of distilled water. Means we will take 25 ml of our master solution and we will add rest of the water to make the solution equals to 250 ml. Means total volume will remain 250 ml. Okay, our second concentration is 0.02 normal. So similarly, by using this equation, I have calculated that we need 50 ml of 0.1 normal KCl, and to make 250 ml solution, we will add 200 ml of distilled water. So similarly, to prepare 0.05 normal solution, by using this equation, we need 12.5 ml of 0.1 normal KCl, means our master solution, and rest of the water we will add to make it up to 250 ml solution. So this is our master solution, which is 0.1 normal, and some amount I have taken in this beaker to prepare the different concentrations. So first I will prepare 0.01 normal KCl from 0.1 normal master solution. For that I need 25 ml of 0.1 normal KCl, so take 25 ml of 0.1 normal KCl,
go.
So I have taken 25 ml of KCl solution. Now I will transfer this solution in this graduated volumetric flask. Now you can see on this graduated flask there is a mark. This mark represents the total capacity of this volumetric flask, and the capacity of this volumetric flask is 250 ml. So to make this solution 250 ml, we will add water. Okay, now I have added 25 ml of our master solution. Now to make this solution 250 ml, we will add water. So here you can see that I am using funnel here to transfer the water into this graduated flask so that water will not spill out, and you have to transfer or to add the water up to the mark. Add water very carefully. So you can see the water level or the level of solution is up to the mark, and always check the lower meniscus. Our second concentration is 0.02 normal. So to prepare 0.02 normal, we will need 50 ml of our master solution and rest of the water. So here we will take 50 ml of master solution and we will transfer it to the volumetric flask. Now to make the solution up to 250 ml, we need 200 ml of distilled water. So fill the water up to mark by using this funnel. So our solution is ready of concentration 0.02 normal.
Go.
Now our third concentration is 0.005. For that we need 12.5 ml our master solution, which is 0.1 normal KCl. So I will take 12.5 ml 0.1 normal KCl solution. So this is my 12.5 ml KCl solution, and I will transfer it in your volumetric flask. Now make the solution up to 250 ml. For that we will add water. We have to fill the graduated volumetric flask up to this mark. This mark represents the total capacity of this volumetric flask, which is 250. So this is our 0.005 normal KCl solution. So we have prepared our all the three concentrations by using the master solution. Okay, now I will tell you about the parts of this instrument. This instrument is your conductivity meter and it is attached with this conductivity cell. This is also known as electrode, which measures the conductance of the given solution, and that conductance value is displayed over here in this instrument. So here you can see there are total 4 controls. This first control represents the cell constant probe. This knob, it is used to set the cell constant value. What is cell constant? Cell constant, it is the characteristics of every electrode of every conductivity cell, and we will synchronize this conductivity cell with this instrument by setting the cell constant value here by using this knob. Now you can see the conductivity, the cell constant of the conductivity cell is mentioned over here, which is 1.036. Now we will use this knob to set this value 1.036 here. Second control is this range. This is known as range. So we will select the appropriate range, which depends upon the expected value of your conductivity of the given solution. So the first range, it represents the 200 micro. This is 2 milli, this is 20 milli, this is 200 milli, and this is 1000 milli. Now third control is temperature. So we will set the temperature which is required for our experiment. Next control is your function. Now here the two functions are important. First is main and second is the cell constant. When we will set the cell constant value, we have to set this knob at the cell constant, right? Then we will set the value of cell constant, which is 1.036, by using this knob here. This setting of the cell constant is known as synchronization of this conductivity cell with your instrument. Okay, so here it display 1.036, which is your cell constant of your conductivity cell. Okay, now this main represent the point at which we will measure the conductance of the given solution. Means when this knob is pointing at main, that means this screen is displaying the conductance value. Now our instrument is ready to measure the conductance values of the different concentrated solution which we have prepared. So first concentration is 0.01 normal KCl, which I have taken in this beaker. This is your 0.01 normal KCl. So how you can measure the conductance value? For that you have to dip this electrode or conductivity cell in the solution. Okay, dip the electrode in your solution and set this knob at mains, which will measure the conductance value, and this conductance value, it will be displayed over here. So displayed value is 5.53 and the range is 20 milli. That means this value is 5.54 milliohm per centimeter. This ohm per centimeter, it represents the unit of your observed conductance. So the value is 5.55. Now we will measure the conductance of our second solution, which is 0.02 normal. For that we have to dip the electrode in this beaker But before that we have to wash the electrode with distilled water to avoid the mixing of two different concentrations. So first of all, wash the, the conductivity cell with distilled water and then dry it by using filter paper or tissue paper. Then dip it in your solution. Now you can see there is a change in the value. Now the conductance of your 0.02 normal KCl solution is 9.23. Always note that value at which it becomes stable. Now just note down this value, which is 9.34, and the unit is millimole per centimeter. Now we will measure the conductance of our next solution, which is 0.005 normal KCl. So for that we have to dip this electrode into this beaker, but before that we have to wash the electrode with distilled water. And then dry it with the tissue paper to avoid any mixing of the two different concentrations. Now dip this electrode in your solution whose conductance is to be measured. Okay, so the observed conductance for this 0.005 normal solution is displaying 3.01 in millimole per centimeter. So your value is 3.03. So this is our observation table. It represents the second column, it represents the concentration of KCl, which is 0.02 normal, and the respective measured value, observed conductance value for this solution is 9.35. For next concentration 0.01 normal, our observed conductance value is 5.55. And for the third concentration, which is 0.005 normal, the observed conductance was equal to 3.03. And the units for the conductance are millimole. These all values are in millimole per centimeter. This is our cell constant, which is 1.036, and with the help of this data we will calculate the specific conductance and equivalent conductance. Now to calculate the specific conductance, we have the formula cell constant multiplied by observed conductance. Because our cell constant is the ratio of specific conductance to the observed conductance. Now by rearranging this expression, you will get the value of specific conductance, which is equal to product of cell constant and observed conductance. Now to calculate the equivalent conductance, the formula is K into 1000 by C. This K is nothing but your specific conductance and C represent the concentration. And we have performed our experiment at room temperature, which is 30 degrees Celsius.